Is there an next? Ah, that's online. Yeah, I was searching. This we saw. Okay, we have the next speaker and the last of this session online, James Hefford, to work together with Maria Roman, optics for premonoidal categories. You can go on, James.
Hi there. Can you all hear me? I hope so.
Let's see. Say a little bit more.
Is that working on your end?
Yeah, it's good.
All right, cool. All right, well, I'm going to talk about, optics for premonoidal categories. This is work with Mario Romano, I think is in the audience there. So if anyone has any questions in person, he's over there. So what were we, sorry, my slides seem to have stopped working. What were we interested in this piece of work? Well, there's a couple of questions we wanted to try and answer. The first was, can we somehow combine together premonoidal categories and promonoidal categories? So in a bit, I'll get into what these two things are, but they're two sort of generalized monoidal-like structures that we can have on a category. Can we somehow combine the two together? And why are we interested in this? Well, one place we might be interested in this is in modeling holes in premonoidal categories. So we understand quite well a category that describes holes in monoidal categories. This is the category of optics. What's the structure of the category of optics over a premonoidal category? What does this look like? So in slightly more detail, we've got promonoidal categories. These are these things that are a bit like monoidal categories, but instead of the tensor product being a functor, the tensor product is now a profunctor. So it takes pairs of things in C and returns things in C, but as a profunctor. And then what's a premonoidal category? Well, instead of being a functor out of the product category, it's a functor out of this thing called the funny tensor product, which I'll sweep under the rug for now. But essentially what this does is it means that not all morphisms in our category interchange with each other anymore. So we lose this interchange law. So we wondered, well, is it possible to define some sort of structure where we combine the two together? So we have a sort of functor that comes out of this funny tensor into C, but it's only a profunctor now instead of being a proper functor. And we looked at this for a bit and we thought, well, you kind of immediately run into a bunch of issues. So you want this structure to be associative, unital, to have these sorts of nice properties. And you look at, say, this equation here, which is giving us the associativity of this structure. And you notice that these x's that we're co-ending over kind of live as parts of this funny tensor product. And what does this even mean? Does this type, what does this, what is this structure about? So we've kind of immediately run into this issue that we're trying to kind of co-end over part of the funny tensor. How do we resolve this? It doesn't seem to really work. And then the other problem we run up against is that for premonoidal categories, these associativity and unital and unit coherence isomorphisms should be central. So they should live in the part of the category that interchanges with all other morphisms. How do we capture that in this setting as well? So that's the one kind of side of the coin. The other side of the coin was we were interested in holes in premonoidal categories. So if I have a monoidal category, I can study kind of the holes in it with this category of optics. And a morphism in this category are these like pairs, this F and this G, quotiented by this equivalence relation that allows us to slide these morphisms U and V back and forth between the two halves. And this category is quite interesting. It has a couple of promonoidal structures. So it has one that allows us to put holes kind of sequentially after each other. And this gives us one promonoidal structure on this category. And it has another that allows us to put holes side by side. But what happens if we replace the underlying category C with a premonoidal category? Well, if we go back to this, we've already got a problem here because this sort of sliding relation of morphisms doesn't really make sense anymore because not all morphisms interchange. So this doesn't really feel like the correct equivalence relation. And in fact, what you probably want to consider is something more like this, where the blue here kind of is to indicate that the only things we can slide back and forth are the central morphisms, those that interchange with everything else. And now this category has been written down before in at least a couple of places. It can be seen as like the category of optics for an action. It rises in sort of mixed optics constructions in the literature. But the full kind of like monoidal-like structure of this category hasn't really been investigated. And moreover, if we were to just consider the center of this premonoidal category, there's a category of optics over that structure. And that embeds into this category. And then how do the two kind of play with each other? Because that one over the center has precisely these two monoidal structures. So we kind of wanted to understand, well, what's the real structure of this category? Okay, so pro-effectful categories are the things that I'm going to spend the next sort of while introducing and working towards. So going way back, what's a monoidal category? Just as a quick recap. Well, it's a category together with this functor that allows us to tensor things. So it takes pairs of things in C, gives us back something in C, and we've got a unit object, and then we ask that this tensor is essentially associative and unital, and we've got a couple of coherence laws. And the first thing to note is that we can replace this unit object with a functor, and this is just a functor that picks out. So it goes from the one object category with one object, one morphism, and just picks out this object I. And then in this world, we can now rewrite these natural isomorphisms in a slightly different form. And what we note is that this thing is a pseudo-monoid in cat. So we have a monoid operation, which takes C cross C to C, and we have the unit of the monoid here. And these are the kind of associativity and unit laws of this pseudo-monoid. And then it's fairly routine to just upgrade this to enrich category theory. So you replace your categories and functors and natural transformations with V categories, V functors, V natural transformations. Replace your products with enriched tensors. And these things are just pseudo-monoids in VCAT. So then what is a promonoidal category? Well, now we replace our functors with profunctors. So instead of having a tensor product that's given by a functor, it's now given by this profunctor. And instead of the unit being a functor, it's now this profunctor. And these are precisely pseudo-monoids in the category of profunctors. And it was Day many years ago who originally introduced these sorts of categories, these structures on categories, and investigated them. And one of the most important things to note about them is that there's an equivalence between these structures on a category and closed monoidal structures on the pre-sheaf category. And this structure is known as Day convolution, and here's what it looks like. So these are on the one side the promonoidal categories. What are premonoidal categories? Well, for this, we have to first introduce something known as a binoidal category. So this is, in some sense, what we're doing here is introducing kind of each half of the tensor product individually. So for each object A, we can tensor on the right by A and on the left by A. And then we want these two different tensors to agree on objects. So this gives us a category with some sort of notion of tensor product on either side. And then a premonoidal, I should say this first. We can talk about which morphisms in this category are now central. So given these tensor products on the left and right, we can define the morphisms that are central to be those that interchange with all other morphisms. And then a premonoidal category takes this structure and makes these tensors essentially unital and associative again. So we have now a unit object, and then the same sort of isomorphisms as before, but these have to live in the center plus the coherences. Okay, maybe an example of a premonoidal category. This is maybe sort of the canonical example in some sense. This is kind of what led Power and Robinson to first defining these categories. As if I take a monoidal category C and consider a strong monad on that category, Then the Kleisli-category of this strong monad is premonoidal. And just give you some idea of why this happens, what the structure is here, is that we on objects, it behaves in exactly the same way as the tensor product on C. But then on morphisms, if we take an F that goes from A to TB, then we define the tensor product with an object C on the right by kind of doing F tensored with 1 on C, and then using one of the strengths to get us back T of something. And you can kind of see from this expression why the structure in general won't be monoidal, for instance, is that if I gave you a G that I wanted to put in here from C to TD, then to get back T of something, I need to do kind of both of the two strengths, the left strength and the right strength. And these things don't, in general, commute. So we can't define this. And you can define this precisely when this monad is in fact monoidal. But one of the kind of not very nice things about premonoidal categories is that algebraically a bit unpleasant. And this is well known to Power and people who first wrote these down. For instance, they're not pseudomonoids in general anywhere nice. The strict ones are, but other than when they're strict, not. So it is possible to combine together like the kind of right-hand tensor and the left-hand tensor bit into one functor. And this is this functor that comes out of this funny tensor. But the problem is that cat actually isn't a monoidal 2 category under this funny tensor. It fails. And if I remember correctly, it's fine on categories and functors, and it fails on the natural transformations. And essentially the problem there is to do with the centrality of those natural transformations. So we can't do the kind of obvious thing you'd want to do here and say, okay, the pseudomonoids in cat with this funny tensor. But what Power introduced that is slightly more algebraically nice are premonoidal categories with a specified set from the outset. And these are known as Freyd-categories, although I will call them effectful categories here. And the idea is that we have our premonoidal category C, and then we pick some monoidal category C0, with our sort of specified center, and then some way of embedding this into the rest of the category. So we have some identity and objects functor that just embeds this center. And it is well understood in the literature how these connect with a whole variety of other structures. So for instance, effectful categories are actually exactly the same thing as strong promonads. So if I give you an effectful category, this J over here, I can write down this expression, and this expression is then a strong promonad on C0. And vice versa, if I give you a strong promonad on C0, I can take the Kleisli category of that promonad, and in a similar way as this example, which was a monad, but you can generalize this to a promonad, define that the Kleisli category is premonoidal, and the free functor into it is an effectful category. They're also, effectful categories are also exactly the same as actions. And these are special actions that sort of extend a canonical one on the center. So we have a center of the category here, which is a monoidal category. So it has an action on itself. And then this monoidal category also has an action on the rest of the premonoidal category. And that has to kind of behave well with the one on the center. And then the final point is that they are in fact pseudomonoids, and Mario spoke about this at ACT last year. And he, as part of his work, he showed that effectful categories are pseudomonoids in the monoidal 2 category of promonads, promonad homomorphisms, and promonad modifications. So I just want to unpack this last point but view it from a slightly different angle. And so it was first Power many years ago who realized that another way of viewing all these structures we're talking about is to use more enriched category theory. So thus far, we've been talking about categories enriched in V, or we can also talk about categories that are enriched in V squared. So this is the category of arrows and commutative squares in V. And if we just unpack all of that somewhat scary sounding definition, what we find at the end of the day is that a V squared category is exactly just an identity and objects functor. And then the V squared functors are the commutative squares of functors, and the V squared natural transformations are kind of ones between each of the components. Although the important bit here is that the components of these V squared natural transformations live in the center of the category, which is really important if we think back to the centrality of the coherence data that we wanted for a premonoidal category. So here's that kind of coming out here, precisely what we want. And this category of V squared categories has itself an interesting generalization of this funny tensor, which is this expression here given by this push out. So if you take JC and JD, you can define their funny tensor to be the diagonal of this push out square. And what you find is that V squared cat is a monoidal 2 category under this funny tensor product. And moreover, an effectful category is precisely a pseudo-monoid in this place. And you might wonder what's happened to this result I told you about a couple of slides ago due to Mario. Well, this is what's happened here is that actually there's just an equivalence of monoidal 2 categories between V squared cat with the funny tensor and this category of promonads, promonad homomorphisms and modifications. Okay, so we can put effectful categories on a similar algebraic footing to monoidal and premonoidal, monoidal and promonoidal categories. They're all pseudo-monoids in different places. So we've got, pseudo-monoid in cat, pseudo-monoid in prof, pseudo-monoid in V squared cat. And what I want to do is define the kind of pro version of this thing to kind of complete the square of these things, if you see what I mean. So what should a pro-effectful one be? Well, you might think, I want pseudo-monoid in something like V squared prof with this funny tensor. This might be our goal, but there's a number of technicalities with this that mean this isn't quite the right definition. And to see why not, to see what kind of goes wrong here, we kind of should take a slight detour into talking about what it means for an effectful category to be closed. So if we recall that a promonoidal category is precisely a closed structure, closed monoidal category on pre-sheaves, then we might hope that a pro-effectful category is something like a closed effectful structure on pre-sheaves. So it makes sense for us to go and study what it means to be closed in this setting. And thankfully, Power gave us a definition of this many years ago, and say an effectful category is closed when sort of tensoring by A on the left or right, these both have right adjoints. So it's very similar to the usual definition, but it involves this functor J in addition to the usual data. And what he showed was that every effectful category, in fact, embeds into a closed effectful category. And what's going on here, in essence, is that if I take my effectful category J, then I can embed C0 into its pre-sheaves and get a closed monoidal category. I've also got this strong promonad on C0. This gives me a strong monad on the pre-sheaf category, whose Kleisli category is premonoidal, because it's a strong monad. And then you can show there exists another functor here and that this makes the square commute. And this gives me an embedding of this into this weird looking functor at the top. And it turns out that this thing is actually, it's not only just effectful, but it's a closed structure. And why is that true? Well, Power went a stage further to give another characterization of this functor as precisely the bijective and objects and fully faithful factorization of the left Kahn extension functor along J. So the thing that takes pre-sheaves on C0, extends them along J to pre-sheaves on C1. I can factorize this into the bijective on objects and fully faithful parts, and up to isomorphism, this LAN L bit, the bijective on objects part, is this F that I wrote before and the Kleisli category up to isomorphism. Okay, what's really going on here in even more abstract terms is that we've got our V squared category J. There exists a pre-sheaf category of this as an enriched category. So this would be adding all of the V squared co-limits. So the V squared co-completion. This guy in the middle is actually just the V co-completion. So we only add the V co-limits to J, not all of the V squared ones. So we get this sort of factorization of the Onadia embedding into this bit into here and then into the full proper pre-sheaf category. And I'll call this the free tight co-completion from now on. Okay, so we've seen how we can take an effectful category and embed it somewhere that's closed and effectful. Our goal is to define something like prof, but we want to really only talk about these tight co-completions. So if we go back to thinking about what prof is, if I have a pro functor from C to D, this is simply a functor from D op tensor C into V. Or equivalently, if I curry this expression, it's something from C into the pre-sheaves of D, where composition is given by this expression here. What's going on here is that this P hat actually looks a little bit like an arrow in a Kleisli category. And in fact, essentially it is. There is a monad, it's technically a relative pseudo-monad, but I'm going to ignore these details for now. There is essentially a monad on cat, which takes these free co-completions, and then if we look at the Kleisli bi-category of that gives us prof. So in our case, if we were to do this with V squared pro-functors, all of them, then we'd have the V squared categories, the V squared pro-functors, which are things into the pre-sheaf category, and then also the natural transformations. But if we recall a moment ago, this pre-sheaf category is not the place that effectful categories embed to be closed and effectful. So what we do is we talk about something that we call the tight V squared pro-functors. And these are simply the ones where the codomain is now only the V co-completion, the tight co-completion of these categories. So this gives us a new bi-category. This is, again, it is a Kleisli bi-category, but it's now for a pseudo-monad, a relative pseudo-monad, we're being very technical, that adds it takes free tight co-completions. Okay, you might wonder, well, what are these tight pro-functors that we've written down? How do these relate to normal ones? So in this setting, you can, a normal pro-functor between these V squared categories can be unpacked into a kind of pair of pro-functors between the two components, plus a natural transformation from P0 into P1 up to these J's. A type one is simply where this is just a natural isomorphism. So it picks out precisely this class of the pro-functors. So with this weird category in hand, one can actually show that this is a monoidal bi-category under this funny tensor product. So one way of doing this would be to say, look at the relative pseudo-monad we defined before and see that this is monoidal with respect to the funny tensor product. And then this shows then that this is in fact a monoidal bi-category as well. In fact, I think it's the case that the category of all of the pro-functors, I mean, I've tried and can't find a way of getting it to work, isn't a monoidal bi-category under the funny tensor. So you really need to do this carving out of this particular bit to get this to work, as far as I am aware. And then finally, we can get to the point where we can define what is a pro-effectful category. Well, it's a pseudo-monoid in this somewhat scary place that we just defined. And at the end of the day, what is that if we unpack all the data? Well, it's a V squared category, so it's its identity and objects functor. It's then a V squared pro-functor of this form. Oh, they should say a tight one. A tight V squared pro-functor of this form, not any old one, a tight one. And a tight V squared pro-functor of this form. So this is kind of doing our tensor products, but it now kind of lacks interchange on the domain here. So it's kind of combining the pre and pro in some sense, and this is our units. Obviously, it's this data plus associativity, unitality, and coherence data because it's a pseudo-monoid. And then we can recover the generalizations of the theorems I mentioned before. So pro-effectful categories are exactly the same as prostrong promonads, and they're exactly the same as pro-actions that extend the canonical pro-action. And of course, we define them as pseudo-monoids in the beginning. So this puts them on a the same algebraic footing in a sense as all of the other structures that we've been talking about. So very briefly, what's going on here is that we now have C0 is now a promonoidal category, which means that its pre-sheaf category is closed and monoidal. We still have the same prostrong promonad here, which means we can get this quasi-category. This quasi-category is premonoidal. And then we've now got this new thing down here, which is this sort of pre-pro combination of the two. And finally, we get to the optics part of this. Will be very brief. Is that if we have a premonoidal category C, we can look at the center of C, and this gives us the embedding of this into the rest of the category, gives us one of these effectful categories. There is then a category of optics over this, which essentially these are kind of non-central things at the top and bottom, but we can only slide central morphisms between them, and then this is the optics of just the center of the category, right, on the left here, plus the embedding of one into the other. And then this category now has two monoidal-like structures. The one of them is putting holes after each other. And there's not really any problem with this. It's just a promonoidal structure like it was before, but in this fully enriched setting. But the horizontal one is a problem because of the lack of interchange. So what we find is that, in fact, it is one of these pro-effectful structures. Yeah, all right, well, I'll leave it there. Are there any questions?
Thank you, James. Are there questions here? Let's see. Online, nothing for now. Okay, yes.
Right, so there's a way to talk about pre-monoidal categories as one object. One object categories enriched in cat with the funny tensor product. Is that right? I might be mixing it up.
Maybe. I mean, this sounds reasonable. I actually don't know off the top of my head.
Yeah. Oh, okay. I was going to ask it. I think it only works for strict, and then I was going to ask if it.
Yes. So strict premonoidal categories are pseudo-monoids in. Yeah, there is a way of viewing those as pseudo-monoids that seems to have escaped me at the moment. But well, they're monoids, right? Because
right, monoids.
Yeah.
So I was going to ask if you can do non-strict by doing something with v-squared prof.
Yeah, I don't know. So you can when you specify the centers of them, but I've never seen a way of turning just a plain premonoidal category without specifying the center into a pseudo-monoid. I don't know that it's possible. I've never. Yeah, this seems to be a recurring problem in some of the literature. People kind of question whether this is possible, and it comes up again. And yeah, I don't know. But it is possible when you specify the center of them. When you specify the center, you get one of these effectful things or Freyd-categories, and these are more algebraically well behaved.
Are there any more questions?
I have one in the room here.
I've got a question. Can people there hear me if I ask my question?
Yes, go on.
So have you, so you gave this definition by defining this very fancy bicategory, I get a monoidal bicategory, looking at the pseudo-monoids there. Have you tried unpacking the whole thing in elementary terms and just sort of
yeah, well,
what it looks like?
So there's a few ways of looking at it. I think maybe the one that's the easiest is this one I've hidden in this second theorem, which is to say that there are these pro-actions that extend this thing on the center. What this is sort of saying is that there are pro-functors that give you an action of this category C0 on C1. on the left and the right, a bit like the tensoring on the left and the right that we had at the very beginning, but these are now pro-functors. So we have this sort of structure, but then we need these to be sort of special ones in the same sense that we did before, which is this extending the action. So C0 has an action on itself as a promonoidal category in prof, in the same way that a monoidal category has an action on itself. And we need kind of the action on C1 to extend that. So this is maybe the most unpacked version. Maybe it would have been wise of me to include that here, but yeah.
Thank you. If there are no more questions, let's thank to all the speakers of this session and also of all the conference. It's brilliant.